Compass theory basically consists of three parts. The first part is called as a free gyro or a free gyroscope. Second part is known as a gravity controlled gyro. And the third part is called as a north seeking damped gyro. So these are the three parts which we are going to do one by one. Today we will first start off with a free gyroscope. We will understand what is this gyro, what are its properties, how does it behave under different situations, and once we understand this, then we will move ahead to controlling the gyro. So ये theory portion cover करेंगे, and after we cover the theory, we will move into the numerical question. Numerical questions are mostly based on the errors of the gyro compass. So that will come later in the second part. So ready हो बेटा? चलें start करें. So with this presentation, we start off with the topic of gyro compass. Now, a gyro compass basically consists of a gyroscope. It works on the principle of law of conservation of angular momentum, and the gyro compass works by utilizing two natural phenomena to provide us with a directional reference. These two natural phenomena are: one, the Earth's incessant or continuous rotation around its axis. Earth completes one round around its axis in 24 hours. So this rotation of the Earth is utilized to make a gyro compass. And second is the force of gravity. So these are two universal natural phenomena which are there in existence. And in making of a gyro compass, we utilize both these phenomena. So now let us try and simplify and understand all these terms one by one. Now at the heart of a gyro compass is a free gyroscope. So let us first of all understand what do we mean by a free gyroscope. You can see a basic gyroscope in this particular diagram. Now a gyroscope consists of a mass in the form of a wheel or a rotor. As you can see in this particular diagram, this yellow color part which is shown in the diagram, yellow color part is the rotor, and this rotor is suspended or fixed in a special arrangement. You can see that it is suspended in such a way that it is free to spin about an axis passing through its center of mass. You can see there is a brown color rod which is passing through this rotor, and this brown color rod is connected to this blue color ring. Now this brown color rod is connected to the blue ring by way of ball bearings, and these ball bearings allow the rotor to spin about the spin axis. You can see this is mentioned in the diagram also. The rotor can spin around the spin axis clockwise or anti-clockwise because of these ball bearings. Also, you will note that this brown rod or the spin axis is fitted in such a way that it passes through the center of mass of the rotor and is perpendicular to the plane of the rotor. The plane of the rotor is represented by the yellow part, and perpendicular to the plane you see this brown color rod which is the spin axis. Moving ahead now, beta. So exactly as we discussed, as you can see in this diagram, the yellow part is the rotor. The brown rod which is passing through the center of mass, center of gravity of the rotor is the spin axis, and this brown rod or the spin axis is connected to the blue horizontal gimbal ring by way of ball bearings. You have a ball bearing fitted at both the ends. This end here shown by the laser pointer and the second end here shown by the laser pointer. These ball bearings provide the freedom to the rotor to spin anti-clockwise or clockwise. Now moving further, if you look carefully at the blue color horizontal ring, you will see that this blue color horizontal ring is connected with the red color vertical ring at two particular points. You can follow the laser pointer. The connection point, one of them is here where the laser pointer is right now, and the second connection point between the blue ring and the red color ring is at this particular point. So the blue horizontal gimbal ring is connected to a vertical red ring through a second set of ball bearings at two particular points, and these 2 points are made in such a way that these are perpendicular to the spin axis. The spin axis brown color rod is here, and you can see the connection point between the blue ring and the red ring are perpendicular to the spin axis, and at these two connection points between the blue ring and the red ring you have another set of ball bearings. Now this second set of ball bearings, which is present in connection of blue and red rings, they allow or permit the spin axis to move in up and down direction. You see, you can pay your attention to the laser pointer. This end of the spin axis can move upwards. This is known as tilting upwards, or this end can also move downwards. This is known as tilting downwards. So this set of ball bearings connecting the blue and red rings allow the spin axis to move up and down, and this up and down motion is known as the tilting motion. If the spin axis is pointing upwards, we say it is tilted up, and if the spin axis is pointing downwards, we say it is tilted down. Now moving further still, if you pay your attention to the red color vertical ring, you will see that this red color ring is connected to the green outer member. There is a green outer member. The red color ring is connected to the green outer member at 2 points. One point is exactly on top of the diagram. This is one point shown by the laser pointer. And the second point where the red ring is connected with the blue outer member is this particular point. Now at these two connection points, we have a third set of ball bearings. So the vertical red ring is connected to a green outer member, and these connection points are at right angles to the spin axis as well as the connection point between the blue and red rings. So right angles to the horizontal axis through a third set of ball bearings. And this set of ball bearings, one fitted on top here connecting the red ring with the green outer member, and one fitted at bottom here connecting the red vertical ring with the green outer member, they allow the spin axis to move in the horizontal plane. You see, the spin axis can move in the horizontal plane. Looking from top, it can move in the clockwise direction like this in the horizontal plane, or it can move in the anti-clockwise direction in the horizontal plane. So this motion of the spin axis in the horizontal plane, in the plane of the blue color ring, is known as drift or drifting motion. So this third set of ball bearings which we have, they allow the spin axis to drift or turn in the horizontal plane. Moving ahead now. Now ideally the spin axis bearings, this three set of ball bearings which we have fitted here, one at the ends of the brown rod, second set at the connection point of the blue and red ring, and third set of ball bearings at the connection point of red ring and the green outer member, one on top and one at the bottom. All these ball bearings should be ideally frictionless so that any rotation which is imparted to the rotor is maintained without any loss. However, practically, whenever you impart any motion to the rotor, there will be some amount of friction. Doesn't matter how well lubricated these ball bearings are, there is going to be a small amount of friction. So to counter that, what is done is we put an electric motor on the rotor just like a normal ceiling fan, and this electric motor maintains a constant RPM on the rotor. So rotor spins with a constant RPM, making this arrangement a free gyroscope. Go ahead, beta.
So this red color was for tilt, and the green color was for drift. What was the blue color for?
Blue color is for spinning, beta. The ball bearings which are fitted on the blue ring allow the rotor and the spin axis to spin anti-clockwise or clockwise.
Okay, sir. And okay. Take it, sir. Okay.
Okay. Now with this particular arrangement, the gyroscope is not constrained in any way so as to alter the direction of its spin axis. It is then said to have 3 degrees of freedom and is called a free gyroscope. So there are 3 degrees of freedom. First freedom is the freedom to spin anti-clockwise or clockwise around the spin axis. You can see this spinning motion shown by this particular arrow. The second freedom is freedom to tilt up and down. The brown color rod can move up and it can move down as shown by the laser pointer. This is known as tilting motion, second degree of freedom. And the third degree of freedom is that this spin axis can move in the horizontal plane, eastwards or westwards. This horizontal plane motion is called as freedom to drift. Combined together, these are known as 3 degrees of freedom, and this particular arrangement is known as a free gyroscope. So a free gyroscope basically has 2 conditions. One, we should have a rotor and spin axis in this particular arrangement fitted with gimbal rings so that the spin axis is totally free to move in whichever direction it likes. And second, the rotor should be spinning with a constant RPM. Once these 2 arrangements are made, we have the 3 degrees of freedom and we have the rotor spinning with a constant RPM. This device converts into a free gyroscope, which is the heart of our gyro compass. Now let me show you this 3 degrees of freedom by way of a animation. You can see we have the yellow color part, that is the rotor, and we have the brown rod in the vertical orientation now. The brown rod is the spin axis. The spin axis is connected with 3 outer rings. So you have a ring in the vertical plane, you have a ring in the horizontal plane, and you have an outer member with handles. So this is a free gyroscope having 3 degrees of freedom. Now, if you look carefully at this animation, you will understand that our spin axis and the rotor and spin axis arrangement is not restricted in any way to move in any direction it likes. Or you can understand it from a different viewpoint. If you apply any force to the outer member, you may move the outer member. It has handles on both the sides. So you may push and pull on these handles. Try to apply any force on the outer member. You will not be able to transmit or transfer this force to the spin axis. The spin axis is basically shielded from any outer force which is being applied to these rings. So it is totally free to move as it likes, and there is no outer force which can be applied to the spin axis if it has this kind of a arrangement. It is shielded from all external forces. Now, having understood a free gyroscope, we can now appreciate the fact that the best example of a free gyroscope in nature is the Earth itself. Earth is the best example of a free gyroscope in nature because it is freely suspended in space, having no friction, thus having all the 3 degrees of freedom. There is nothing which is restricting the Earth to change its direct direction of the axis. So it has all the 3 degrees of freedom and can move as it likes. The Earth is heavy and well balanced, with the equatorial mass corresponding to the plane of the rotor. Now we know the Earth is slightly flattened at the poles and is bulging at the equator. So the equatorial mass is more as compared to the polar mass. So with this equatorial mass corresponding to the plane of the rotor, it is perpendicular to the axis around which the Earth is rotating. So it corresponds exactly to the rotor and spin axis arrangement which we saw in a free gyroscope. Earth also rotates at a considerably high speed about its axis, which is equivalent to the spin axis of a rotor. The Earth rotates by 360 degrees in a period of 24 hours in one day, which converts to 15 degrees of motion in 1 hour. If you are at the equator, the Earth's rotation covers 15 degrees of d-long in 1 hour, and that converts to, at the equator, it converts to 900 miles per hour. 1 minute of longitude is equal to 1 minute of latitude, equal to 1 nautical mile at the equator. And the speed at which the Earth is taking the observer who may be present on the equator is a speed of 900 miles per hour or 900 knots. As we move away from the equator and go toward the pole, the speed starts to reduce slightly, but you can check the speed with which the Earth is moving with a formula of 900 cos latitude. So at the equator, 900 knots is the speed. At any other particular latitude, the speed can be calculated by the formula 900 cos of lat. Now, having learnt about a free gyroscope, we are now moving into the special properties of a free gyroscope. We know that a free gyroscope consists of a rotor and a spin axis having 3 degrees of freedom. Freedom to spin clockwise or anti-clockwise, freedom to tilt up and down, freedom to drift east and west. Now, as soon as we make a free gyroscope, we have the 3 degrees of freedom and the rotor is imparted some angular velocity. It starts exhibiting 2 special properties. These are gyroscopic inertia and gyroscopic precession. We are now going to understand these 2 properties one by one in detail. Now, starting with the first property of the free gyroscope, that is gyroscopic inertia. We have the same gimbal arrangement which I showed you earlier. Gyroscopic inertia defines that a freely spinning gyroscope will maintain its axis of spin in the same direction with respect to space, irrespective of how its supporting base is turned, and it resists any attempt to change the direction of its spin axis. Now, as you can see in this particular animation, that the base or the outer member, which is having these two handles attached to it, the supporting base or the outer members as well as the gimbals are turning, but the spin axis maintain its direction. This happens because of gyroscopic inertia. You can move the outer member holding it by these handles in any particular direction you may like, but the spin axis will continue to maintain its direction of spin. Now, very important thing in this property is that the spin axis maintain its direction with respect to space. It is not with respect to the earth, it is with respect to the space. Now, it may not be making much sense at the moment, but later when we go into understanding of the gyro compass, it will become very clear to you what is the significance of this word or this term, that the spin axis maintains the same direction with respect to space. Even if you try to push the brown color spin axis directly, let us say you try to touch the spin axis, the brown color rod, and try to push it manually bypassing these gimbals, the outer member and the gimbals, even then you will feel that it will resist any attempt to change the direction of its spin axis. If it was not spinning and you push the brown color rod, it will move in whichever direction you are pushing it. But as soon as it starts spinning and showing this gyroscopic inertia, even if you push it, it is going to resist any attempt to change its direction. You will see that a resistive force appear, invisible resistive force appear. So thus we can say that a free gyroscope has high directional stability. This is known as gyroscopic inertia or rigidity in space or directional stability. This property can be denoted by any of these terms: gyroscopic inertia, rigidity in space, or directional stability. All three of them mean the same. The gyroscopic inertia of a rotor can be quantified. How much is the gyroscopic inertia of a particular rotor? It depends on its angular momentum. The greater the angular momentum of a rotor, the greater will be the gyroscopic inertia exhibit by the gyroscope. The angular momentum depends upon the mass of the rotor and the distribution of the mass. So the quantity, how much gyroscopic inertia is present in a particular gyroscope, is dependent upon what is the angular momentum of that gyroscope. Let's move to the second property now of the free gyroscope, which is known as gyroscopic precession. Now, as we just now discussed, under gyroscopic inertia property, that a free gyroscope is going to resist any attempt to change its direction of spin. However, if we go on increasing the force which is being applied, this resistance cannot match up with the applied force infinitely, and at some point of time, the spin axis will eventually move. To give you an example, let's say we have made a free gyroscope with a cycle tire, and we have imparted it some rotational velocity, and it's moving now. You try to change the direction of its spin axis, it is going to resist any attempt. But let's say you were alone and you were trying to change its direction. It was resisting the attempt. You call your friends. So there are three of you now. Now all three of you try to change its direction of spin. Eventually, at some point of time, you can overpower it. You can overpower its gyroscopic inertia. Now, when you overpower its gyroscopic inertia, it is going to move. The movement of the spin axis when a force is applied on it and the force is powerful enough to overpower its gyroscopic inertia. This movement of the spin axis is known as gyroscopic precession. So this is the definition of gyroscopic precession. The movement of the spin axis when a force is applied on it is known as gyroscopic precession. Now going further in gyroscopic precession, we will try to understand it from diagrams. Now the way in which the spin axis moves is quite surprising. We would expect it to move in the direction of the applied force. That is how normal bodies move. Let us say if you have a chair placed in your room and you push it in a certain direction, the chair is going to move in that direction in which you are pushing it. So we would expect the spin axis to move in the direction of the applied force. But the motion is not in that direction. The motion is at right angles to the applied force. Now, if you talk of right angles, then there will be two directions. If you are applying a particular force, there will be two directions at right angles to the applied force. So in which direction will the spin axis move? It will be at right angles to the applied force in the direction of the spin of the rotor. Now this is a little difficult to understand theoretically. Let's try to understand using a diagram. So you see a rotor here. The rotor is moving in the clockwise direction. If you are looking from this particular side, where you have this arrow, looking from this particular side, the rotor is moving in a clockwise direction. Now, as you can see in the diagram, this arrow represents the force which is being applied. So on this end of the spin axis, we are applying a force in the upward direction. And we would expect the spin axis to move upwards. The spin axis should be moving upwards. But the motion of the spin axis will not be in this particular direction. So a force is being applied to the spin axis, this end of the spin axis in the upward direction. That means in the vertical plane. But it will be moving in a surprising way. The motion of the spin axis will not be in the vertical plane. The motion of the spin axis will be in the horizontal plane. How will the motion be? The spin axis is not going to move up. What the spin axis is going to do is, see, it is rotating clockwise. So it will move in such a way as if this force has been turned by 90 degrees in the direction of spin. So if it was being applied in this particular way, the rotor is moving clockwise. It will move as if the force has been turned 90 degrees and it is being applied in this particular direction, like this. So you are applying the force in this particular way, and the spin axis will move like this. You see this particular arrow being shown here. The force was trying to move the rotor in this particular direction, but it will turn 90 degrees in the direction of spin, and the spin axis will move in the horizontal plane. Now, it may be a little difficult to understand from the diagram, so I will be showing you a video later on where it will become more clear to you.
सर प्लीज सर ये समझ में नहीं आया सर प्रिसेशन थोड़ा.
Okay, beta, don't worry. I'll show you a video. We will understand it. Give me a minute. I'll show you.
This is a gyroscope. It consists of a metal wheel mounted on an axle.
Is the audio video working well?
Yes sir, yes sir.
Okay, all right.
The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes.
Okay, beta. Now, if you look at this equipment carefully, you see there are some outer handles which he is holding in his hands. These are known as the outer members. And you see this green color ring. This green color ring is what spins. The outer members are not moving at all. The green color ring is spinning. And this green color ring is basically connected with this rod up to here. Okay, up to this point. So this rod is also spinning. And this entire rod from one end to another end, it has ball bearings inside it. And these ball bearings are very well lubricated. In fact, you can drop the lubricating oil also from the sides to keep it well lubricated. So once you impart some spinning motion to it, it keeps on spinning for a long, long time.
A string provides a simple method to spin the wheel.
I hope you can see that, beta. The green color wheel and this associated pipe up to here is connected. And this entire thing is spinning. Able to understand?
Yes sir, now.
Okay, great.
The first thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it...
Okay. So the first thing what he notices is that a resistive force appears. Whenever he is trying to turn the spin axis, there is a resistive force. I don't know whether you have seen a toy which children use. It's called fidget spinner. So have you used it anytime, beta? Fidget spinner?
Yes sir.
Okay, great. So if you have used the fidget spinner, you will know that as soon as you spin it, it becomes little heavy. You cannot turn it freely. So that fidget spinner is nothing but the example of a free gyroscope. And why it becomes heavy is because it attains some gyroscopic inertia. it will resist any attempt to change the direction of the spin axis. So that is the first thing which he has noticed here. Now let us see more properties.
Position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright. When the wheel stops,
so now it is not falling because of gyroscopic inertia. The gyroscopic inertia keeps the spin axis pointing in that fixed direction. Now when the spinning becomes less, the motion dies down, then the gyroscopic inertia will be lost and then it's going to fall down.
the force disappears and the gyroscope falls. Incredibly, this force will support the gyroscope like this. It appears to be levitating.
Now this is gyroscopic precession beta. You see, one of the ends of the spin axis is supported on this particular stand and the other end is free. Now if it was not spinning, the free end would immediately fall down. Gravity would make the free end immediately fall downwards. But what is happening now? The force of gravity is trying to push it downwards, but because of gyroscopic precession, it turns by 90 degrees and it starts moving the spin axis in the horizontal plane. It does not fall in the vertical plane, but it moves in the horizontal plane.
A spinning gyroscope will balance on a string. You can even lift the gyroscope with a string looped around one end.
Now if it was a normal object, the free end would immediately fall down because of gravity. But now gravity is trying to push it down. The force gets turned by 90 degrees in the direction of spin and it starts moving in the horizontal plane.
This interesting behavior is difficult to explain. Physicists have determined that a rotating wheel has angular momentum, similar to the momentum that a stone flying through the air has.
Okay, all right. So were you able to understand, beta?
Yes, sir.
Okay, great. Let me show you another clip. It'll make it all the more clear. Give me a minute.
Sir, question.
Just a minute, beta. Go ahead, beta. Go ahead with the question.
So you did definition and that whatever force we apply, the resultant will appear at right angle. So basically, can we simplify it by saying if we apply a vertical force, if we apply a force in the vertical plane, resultant will be in horizontal plane and vice versa?
No, the things can be in between horizontal and vertical also. Okay, there can be many other possibilities also. I'll try to show you here. I have a small model, beta. Okay, you will not be able to see it. Let me change the background settings. 1 minute. Okay, all right. I have a small model in my hand. So this, you see this particular marker, this is the spin axis and you can see the rotor also. Okay, मैंने rotor पे बेटा ये arrow marks भी लगा दिए हैं just to show the direction in which it is spinning. So I hope you can see the model. Clear? Okay, all right. Now let us say we apply a force on this part of the spin axis. This is like this. This is the spin axis. Okay, SIA. So if I apply a force in this particular way, the gyroscopic precession says it will not move like this. A normal object would have moved like this if I apply a force. It will not move like this. It will turn 90 degrees in the direction of spin. So the arrows show us the direction of spin. It will move like this. 90 degrees it has turned, and it will apply a force in this way. Okay. So you push it down. It is not going to go down. It's going to spin in this way. Okay. Now look at a different scenario. If I change the direction of spin, right now from your side it is anti-clockwise. If I change it, so let me change it. Now you see this particular end of the spin axis, and the motion is now clockwise. Okay, it is like this. I hope you can see it well. Now if I apply a force this way, okay, let me use the other hand. If I apply a force this way, it will turn this particular direction in the direction of spin, and it will get moving in this way, like this. Okay, so were you able to make out beta gyroscopic precession? Okay, great. Now let me show the same thing to you using another clip. Give me a minute. Okay, all right. Let's see this one.
Good evening. I'm Ed. This is an egg chop production, and we're going to demonstrate a gyroscope spinning. Now, over here we have a brass gyroscope, toy gyroscope. There's a brass flywheel that rotates in this.
So you see, beta, we have the spin axis, we have the rotor, quite thick rotor. It's a brass rotor, and you can see that he has now turned it, and it is spinning. Okay, it can spin clockwise or anti-clockwise in any direction. You see the ends of the spin axis are contained within a horizontal ring. You have a horizontal ring, and the horizontal ring is connected with a vertical ring. The vertical ring is not complete. They have only shown half the ring. So this vertical ring is cut. It's not a complete ring. It's a half ring. And again, at the bottom of the vertical ring, you have a stand. And there is a ball bearing between the vertical ring and the stand also.
Axis, and it's on the gimbal. And the gimbal is made to spin around this axis.
Okay. Now this, what he has done just now, is known as freedom to tilt up and down. The spin axis can move up and it can move down. I'll show you once again.
And the gimbal is made to spin around this axis.
This is freedom to tilt up and down.
And also on a vertical axis this way.
This is called as freedom to drift in the horizontal plane. The spin axis can move in the horizontal plane. This is known as freedom to drift.
Now,
okay, before we proceed ahead, beta, 3 degrees of freedom are clear. Freedom to spin clockwise and anti-clockwise, freedom to tilt up and down, freedom to drift east and west. Any doubt in these three?
No, sir.
Okay, great. Very good. Let's move ahead.
What I'm about to do is spin this gyroscope using a Dremel with a little rubber wheel on this. And I can get this to spin about anywhere between 3,000 to 6,000 revolutions per minute. And with the gyroscope spinning, it becomes stable and wants to resist movement. As a matter of fact, it's going to prevent me from trying to move it in this axis. So here we go. I'm going to start this gyroscope spinning. Again, clockwise from your motion going like this. I also put some spiral marking on the flywheel so you can see that the gyroscope will be moving.
So this shows the spinning motion. You see these spiral lines and you can see that it is spinning.
All right, here we go. There we go. Now the gyroscope is spinning about 3,000 RPM in this axis. And as you can see, if we try spinning this gyroscope around this axis, it's going to want to resist movement. Here we go. Let's see what this gyroscope wants to do if we try to spin it in this axis. There we go. I'm going to try pushing the gyroscope the other way, pushing the right-hand side of the gyroscope towards you, and you're going to see what it's going to want to do.
This is what is gyroscopic precession, beta. If you look carefully, he is applying a force in the horizontal plane, trying to turn the spin axis in the horizontal plane, but the spin axis moves in the vertical plane. This is gyroscopic precession. So let me show it to you once again.
There we go. I'm going to try pushing the gyroscope the other way, pushing the right-hand side of the gyroscope towards you, and you're going to see what it's going to want to do. There we go. Now, if I...
Okay. So is that clear, beta? अब समझ में आ गया precession?
Yes, sir.
Okay, all right. Any doubts in precession and gyroscopic inertia till here?
Sir.
Go ahead. Any doubts?
Yes, sir. So when they applied the force on the rotor itself, it moves in the east-west direction, correct, sir? On the body of the rotor. As per the slide which you have shown, previous slide which you have shown, sir.
Okay, let's go back to the slide, beta. इसमें वीडियो में तो डाउट नहीं है बेटा?
No, sir. Video में तो doubt.
Okay, all right. So let me show you the slide. Give me a minute. अच्छा, वीडियो बेटा रिपीट तो नहीं देखना. I hope it is clear now.
Yes, sir.
Okay, all right. Let's go back to the slide. Okay. Here we are, beta. Are you talking about this diagram?
Yes, sir. You see that you see where you have applied force on the body of the rotor, correct, sir?
Right.
And when you apply body on the force of the rotor, the one axis which is pointing towards the east is moving towards the north direction, correct, sir?
Okay. We are applying a force on the spin axis at this end. I hope you can see the cursor.
Okay, but you have okay, sir. Okay.
So this indirectly means that the force is getting applied to the rotor as you see at the top. This is how the force is getting applied. Okay.
Okay, sir. When you are tilting the spin axis, it is going in the east-west direction. The reaction is on the east-west direction. Correct, sir?
ओके बेटा, अभी इस डायग्राम में हमने कोई भी नॉर्थ साउथ ईस्ट वेस्ट शो नहीं किया है, so you can't say in which
Okay, it is drifting basically to.
you can say it is going, it is, see, if you look at the spin axis, it is trying to push the left end of the spin axis up. If you look at the rotor, it is trying to push the top end of the rotor to the right side of the screen.
Correct.
Right. Up to here is okay.
Yes,
so
sir.
after this, the force turned by 90 degrees in the direction of spin. So you see this arrow here shows the direction of spin. It is moving clockwise viewed from the left end of the spin axis. So it gets turned by 90 degrees and it applies the right end of the rotor in this particular way. Or you can say it is pushing the right side end of the spin axis into the screen.
Oh, okay, sir. Which the direction
Okay.
which you are moving the cursor, that end will move
Yes.
towards the direction of the cursor. When you are applying
Yes.
an upward force, that end will move to the direction which you are moving the pointer.
Exactly. Now you can see it here also. See, the force is being applied upwards. You see, this is the plane of force in which the force is being applied. This is the plane in which the force is being applied. You see here, plane
Yes, sir.
of force. And the movement of the spin axis is in this particular plane, this plane, the horizontal plane. That is why you see it is mentioned as the plane of precession.
Plane of precision. Okay, sir.
Okay, beta, clear हुआ?
Yes, sir. Now I got the diagram clear.
Okay, great, very good. So यहाँ तक clear है बेटा? चल सकते हैं आगे?
Yes, sir.
Okay, great. So I'm changing the presentation now, closing this one. So बेटा, ये है हमारा पहला important concept. We need to know what is a free gyroscope, and then we need to understand its two properties, gyroscopic inertia and gyroscopic precession. Once you have understood that, so you have understood the basics. Now we are going to use these basics to make a gyro compass. Till the end, ये जो basic properties हैं, इनको हम use करते रहेंगे. So let's go ahead. Let me now take you further. Okay. अब मुझे आपको एक और वीडियो दिखाना है. Okay. Now बेटा, understand. हमने अभी देखा है that we have this rotor and spin axis arrangement. Go ahead बेटा.
Sir, I have studied, I have taken example of the earth, like earth has a movement in altitude and the horizontal movement. From altitude, from vertical movement, the altitude changes, and from horizontal movement, azimuth is changes. So if we apply force against the altitude, it starts moving through the horizontal plane, that is 90 degree. And if we
That's
apply force against the horizontal, it starts moving vertically up and down. That's what it is.
Perfect बेटा, you are right. Okay, great. So अब बेटा देखो, मैंने आपको जायरोस्कोपिक इनर्शिया की प्रॉपर्टी बताई है. जायरोस्कोपिक इनर्शिया सेज कि अगर आपके पास एक रोटर और स्पिन एक्सिस अरेंजमेंट है and you make it point towards a fixed direction, like you see this is now pointing towards a fixed direction, इस डायरेक्शन में पॉइंट कर रहा है, it will remain pointing towards that direction with respect to space, not with respect to earth, with respect to space. इसका मतलब ये हुआ कि मेरा जो ये स्पिन एक्सिस है, ये स्पेस में जिस डायरेक्शन को पॉइंट कर रहा है, ये उसी डायरेक्शन में पॉइंट करता रहेगा. अब बेटा जो स्पेस है या जो सेलेस्टियल स्फीयर है, उसमें जो डायरेक्शंस हैं, डायरेक्शंस, they are basically represented by stars. Stars are fixed objects in space. Stars are fixed objects. They do not move. To us, they appear to be moving. Star rise करते हैं, set करते हैं. That is because of the rotation of Earth. That is why stars appear to move. Okay. Now, stars are actually not moving in the sky. The stars are fixed. You can check it from the almanac also. The SHA and declination of the stars remain same. So if we say that this spin axis is pointing towards a fixed direction in space, so it means that if it is pointing towards a particular star, it will keep on pointing towards that star. Okay. And as the stars moves in the sky because of the rotation of the earth, the spin axis will also keep on following the motion of the star. So indirectly इसका मतलब ये हुआ कि अगर आप ये spin axis arrangement को एक particular star की ओर point करके छोड़ देते हो, जैसे जैसे वो star move करेगा वैसे वैसे हमारा spin axis उसको follow करेगा. This is the meaning of gyroscopic inertia. The spin axis points in a fixed direction with respect to space. Stars are fixed objects in space. Wherever the star goes, the spin axis follows. और जब भी हम एक रोटर और स्पिन एक्सिस अरेंजमेंट को एक्टिवेट करते हैं, एक फ्री जायरोस्कोप बनाते हैं, whichever direction it is pointing, whatever star is there, we call it as our gyro star. So up to here is clear, beta? Okay, all right. So we have seen our spin axis will remain pointing towards a star. जैसे जैसे स्टार मूव करेगा वैसे वैसे हमारा स्पिन एक्सिस भी मूव करेगा. अब हमें इस फ्री जायरोस्कोप को एक जायरो कंपास में कन्वर्ट करना है. सो वी नीड टू अंडरस्टैंड द मोशन ऑफ द स्पिन एक्सिस. We don't want this motion. We want to make it point towards a fixed direction with respect to Earth. So हमें इस motion को control करना है बेटा. इसको control करने के लिए first we have to understand how is this moving. Now to easily understand how the spin axis is moving, it is very easy to understand by looking at the motion of a star. We are navigators. We know how stars move. We have been doing star numericals, PZX triangle, rational horizon in phase 1. So the same concept, how stars move in the sky, can be used here also. So this is what we are going to do. Only thing is we will not make a rational horizon diagram here. We will see the motion of the stars from the earth. How do they appear to move? That will give us an idea how the spin axis moves. And once we get an idea how the spin axis is moving, we can control it easily. So अब इस चीज को understand करने के लिए, to understand how stars move in the sky, what I did was I put a camera in the night pointing towards the north direction. अपने घर की छत पे मैंने एक कैमरा लगा दिया pointing towards the north direction, and this camera recorded the motion of the stars. I made a time lapse video. So full night का एक time lapse video बनाया. So in that video, it is like you see the targets moving on the radar with trails on. So you can see the motion of the stars. So I'm going to show you that video. The camera is pointing towards north and it is capturing the motion of the stars in the sky. So let me take you to that video. Give me a minute. How does the motion look like? Now you can see the motion of the stars, beta. You see there is one particular star which is not moving at all, where the cursor is right now. So can you guess which star is that?
Polaris.
Very good, beta. Great. That is the Polaris or the pole star. All other stars are moving around it. Let me take you back. See this once again. So this is Polaris here. All other stars are moving around it. And you can see that the stars are moving in a anti-clockwise fashion or anti-clockwise motion. You can consider that the bottom of the screen, if it is the horizon, bottom of the screen is the horizon. This is how the stars are moving in the sky. It's a circular motion and this circle is centered at the pole or the pole star, Polaris. So clear beta, the motion of the stars is clear. Great. Now keep this thing in your mind. This is how the stars move. इसको ध्यान में रखना. इसी के बेसिस पे अब हम हमारे स्पिन एक्सिस की मोशन को अंडरस्टैंड करने वाले हैं. So let's go. I'm going to stop the video now. Now we have understood a free gyro. What is a free gyro? And we have understood its two properties of gyroscopic inertia and gyroscopic precession. Also, we have seen the motion of the stars in the sky. We know how the stars appear to move in the sky because of the rotation of the earth. Now, what you see on the screen is a still picture of the sky showing a time-lapse picture of the sky showing the motion of the star. So you see all these concentric circles representing different stars, and all these concentric circles are centered at a particular point, and this point which you see at the center is the pole. Now with these things clear in our mind, we are now going to understand how is the spin axis of a free gyro going to behave or going to move with respect to the earth surface. So let's try to understand that. So first thing, the center of all these concentric circles is the pole. We are aware all the stars, they move in concentric circles, which are basically their declination circles around the pole. So let us mark the center of all these circles as the pole. Now this picture is taken on land. This is basically the camera pointing towards the North Pole, capturing the horizon as well as the motion of the stars. It is a time-lapse picture of the motion of the stars. So because it is taken on land, the horizon is not very clear. So let's mark the horizon in this diagram. You can see this blue color line appearing at the bottom. This represents the horizon of the observer. So this is the horizon. Now let's assume that we have a free gyro and we want to have a gyro compass which can give us a direction reference. Now we want our free gyro spin axis to point towards north. So let's first identify the north point on our horizon. Now if we come vertically down from the pole, the point where it touches the horizon, that is the north point of our horizon, of the observer's horizon. So you can see this yellow color vertical line passing from the pole. Wherever this line touches the horizon at this particular point, this is the north point of our horizon. So we want our spin axis to point to north. Now if we go to this vertical line, the yellow color line which we see, basically represents the meridian of the observer. So let's mark this line as the meridian. This represents the meridian of the observer. The meridian passes from the pole. Now if N is the point representing the north direction, if we go towards the right hand side, this represents the easterly direction. So you see the easterly direction coming up on the right side of the diagram. And from point N, if we go towards the left hand side in this particular direction, this represents the west direction. So east and west also identified in the diagram. Now let's assume we have a free gyro and we want to make a gyro compass with it, and we align the spin axis of that free gyro to the north point on our horizon. This is our directional reference, the north point on our horizon. So I point the spin axis of my free gyro to this end point. Now, if my gyro spin axis is pointing towards this particular point, the end point in the diagram, November point, that means my gyro star is also going to be here. So you can see the gyro star in the diagram now. We have shown the gyro star at particular point N. Now we have the gyro star. We can also show the motion of the gyro star. We know all the stars will be moving on concentric circles around the pole, and they will be moving in an anti-clockwise direction. So let me now show you the declination circle of the gyro star. So you can see this declination circle of the gyro star, the yellow color circle. The arrow represents the direction in which the star will be moving. So this is the declination circle on which our gyro star will be moving. Now once we leave our spin axis pointing towards the November point or towards this particular gyro star, after this the gyro star is going to move on its declination circle, and after about approximately 6 hours, this is where you will have the gyro star. You can see it represented by point A in the diagram. So after 6 hours, our gyro star is going to be at this particular location. After this, it is going to move further on its declination circle, again shown by the arrow, the yellow color arrow on its declination circle. And after about 12 hours, the gyro star is going to be at this particular location. This is point Bravo. The gyro star is going to reach at this particular location after 12 hours. So from point Bravo, the gyro star is going to move further on its declination circle, again shown by the yellow color arrow. And after about 18 hours, the gyro star is going to be at point Charlie, point C in our diagram. This is where the location is. This is the position where the gyro star will be after 18 hours. And if we keep on observing it further, it will again move on its declination circle, and after 24 hours, it is going to come back at point November. So a complete declination circle of the gyro star covered in 24 hours, and it has come back to November. And day after day, our gyro star will keep on repeating this motion. Now, if our gyro star is making this kind of a motion, because of gyroscopic inertia, the spin axis is also going to follow the gyro star. So when you set it at point November, after 6 hours, as the gyro star comes to point alpha, our spin axis is also going to point towards point alpha, position alpha. Now, if you look carefully, the motion of the gyro star between November to alpha, the gyro star is increasing its altitude. That means the spin axis tilt is also increasing in value. So gyro star increasing its altitude, the spin axis tilt is exactly same as the altitude of the gyro star. So the tilt of the spin axis will also be increasing. Or you can say the spin axis will be tilting upwards. From November to alpha, the spin axis will be tilting upwards. You can see this coming up here. The tilting of the spin axis will be upwards. The second thing which we note, when the gyro star is going from November to alpha, it is changing its azimuth in the easterly direction. At point November, the azimuth was 0, 0, 0. And as it moves towards point alpha, the azimuth is moving or changing in the easterly direction. The star is moving towards easterly direction. Now the azimuth of the gyro star represents or refers to the drift of the spin axis. So spin axis will also be drifting in the same direction, that is the easterly direction. So from November to alpha, the spin axis will be tilting upwards, and it will be drifting in the easterly direction. So this motion is going to take 6 hours. After 6 hours, our gyrostar is going to move from point alpha to point Bravo. Now when the gyrostar is moving from alpha to Bravo, its altitude is still increasing. So the gyrostar is moving upwards in the sky. So the tilt of the spin axis will also be increasing. So it will also be tilting upwards. From point alpha to point Bravo, between 6 to 12 hours, the spin axis of the free gyro will be tilting upwards. You can see this coming up in the diagram. And the second thing which you notice, when the gyrostar is moving from point alpha to point Bravo, it is moving in the westerly direction now. See, the left side in the diagram is the westerly direction, and star's azimuth is now moving in the westerly direction. So the spin axis will also be drifting westerly. Now after point Bravo, the gyrostar is going to move from Bravo to Charlie. When it is moving from Bravo to Charlie, you can now observe that the altitude of the gyrostar is decreasing. The altitude is decreasing. It is coming down in the sky. So that tells us that the tilt of the spin axis will also be decreasing. The spin axis will also be moving downwards. So we can say that the spin axis is tilting down. And another thing which we notice, when the gyrostar is moving from Bravo to Charlie, it is moving in the westerly direction. It is moving towards the left side in the diagram, and the left side represents the westerly direction. So that tells us that the drift of the spin axis will also be changing in the westerly direction, or you can say the spin axis will be drifting westerly. The drift of the spin axis basically refers to or corresponds with the azimuth of the star. So azimuth moving westerly, the spin axis is also drifting westerly. Now moving from Charlie to November, you can see the gyrostar is decreasing its altitude. The altitude of the gyrostar is decreasing, or it is moving downwards in the sky. So that tells us that the spin axis will be tilting down. So you can see it coming up. Spin axis will be tilting down. Also, if you notice, from point Charlie to point November, the star's azimuth or star's direction is now, it is moving in the easterly direction. It is moving towards the right side of the diagram. The right side of the diagram is the easterly direction. So the drifting of the spin axis will be easterly. So to summarize, from November to Alpha, tilting will be upwards, drifting will be easterly. Alpha to Bravo, tilting will be upwards, drifting will be westerly. From Bravo to Charlie, tilting will be downwards, drifting will be westerly. And from Charlie to November, tilting will be downwards and drifting will be easterly. Our spin axis is going to follow this particular motion of the star day after day, completing one oscillation or one round in 24 hours or in one day. Any doubts coming up to here, beta? Okay, beta. Great. Now, two very important things to notice in this motion of the gyrostar or motion of the spin axis are, you see in this particular diagram, the vertical yellow color line which we have represents the meridian of the observer. And if you watch carefully, whenever the gyrostar is east of the meridian, that is from point November to point Alpha to point Bravo. This semicircle is east of the meridian. Right side is the easterly direction. Whenever the gyro star is east of the meridian, you see it is always moving upwards in the sky, or its altitude is always increasing. So this tells us that the tilting of the spin axis will be always upwards east of the meridian. And if you look carefully, after Bravo, the gyro star goes west of the meridian, from Bravo up to Charlie, and then up to November. Bravo to Charlie to November, this semicircle is made to the west of the meridian. And whenever the gyro star is west of the meridian, you can see its altitude will always be decreasing. If the altitude is decreasing, this tells us that the tilting will always be downwards west of the meridian. So the spin axis tilting will be downwards west of the meridian, and spin axis tilting will be upwards east of the meridian. The second important thing to note is we have the pole in this diagram at the center of the declination circle. Now let's draw a line showing the altitude of the pole. You see this green color line here in the diagram. This green color line basically shows all the points at the same altitude at the pole. Now if you look carefully, whenever the gyro star is above this green color line, it is moving in the westerly direction. You see, from Alpha to Bravo, it is moving in the westerly direction. Westerly direction is the left side in the diagram. So from Alpha to Bravo, it is moving westerly. From Bravo to Charlie, it is again moving in the westerly direction. So this tells us that the drifting of the spin axis is going to be westerly from Alpha to Bravo to Charlie. And if you look carefully, this semicircle Alpha to Bravo to Charlie is when the gyro star is above the pole. Whenever the star is above this green color line, it is said to be above the pole, or in other words, its altitude is higher than the altitude of the pole. And whenever the star is below this green color line, it is said to be below the pole, which means the altitude of the gyro star is less than the altitude of the pole. So we come to a conclusion here. Whenever the gyro star or spin axis is above the pole, the drifting is going to be westerly, and it is happening from Alpha to Bravo to Charlie. Now once the gyro star crosses Charlie, it comes below the pole, and you see when it crosses from Charlie going towards November, it is moving in the easterly direction. Also from November to Alpha, it is moving in the easterly direction. So whenever the gyro star is below the pole or its altitude is less than the altitude of the pole, it will be moving eastwards. So that tells us that whenever the spin axis is pointing below the pole, the drifting will be easterly. So from Charlie to November to Alpha, the drifting is easterly. Now these are very important to understand the making of or converting of a free gyro into a gyro compass. Once we know these directions, it makes it very, very easy to understand how a free gyro is converted into a gyro compass. Now moving further in our explanation, we have seen the tilting and the drifting motion of the spin axis. As the altitude and azimuth of the gyro star changes, it keeps on tilting upwards or downwards, it keeps on drifting eastwards or westwards. Now, we have formulas which are available to us with which we can find what is the rate at which the spin axis is going upwards or coming downwards. And we can also find out what is the rate at which it is moving in the easterly direction or westerly direction. So what is the magnitude of tilting, or how fast is the spin axis going up or down, and what is the magnitude of drifting, or how fast the spin axis is going easterly or westerly, can be found using formula which we will see one by one. Any doubts up to here, beta?
सर ये जो फ्री जायरोस्कोप डायरेक्शन हम पॉइंट करते हैं, this direction is towards the pole or we are taking it or at that star as you have explained in this diagram?
ओके बेटा, आप इसे अभी तो हम सिर्फ इसकी मोशन को अंडरस्टैंड कर रहे हैं. Basically, once the gyro compass is made, we will not be required to point it to any direction. It will automatically point towards north. अभी के लिए तो हम इसकी मोशन को अंडरस्टैंड कर रहे हैं. So wherever you take it, it is going to make a circle like this. अगर आप इसे पोल पे ही रख दोगे तो फिर तो बहुत सिंपल हो जाएगा. It is going to point there only. Okay, but you cannot do that and make a compass, because अगर आपने उसे पोल पे रखा और कंपास बना दी, tomorrow if there is a blackout and if it gets disturbed from that position, तो दोबारा इसे पोल पे एडजस्ट करना जो है, that will be very very difficult. You will need another compass to do it.
Okay, sir. And sir, this relative motion of the star N, A, B, C, this is due to rotation of Earth.
Yes, that's correct, beta. This is due to the rotation of the Earth. The star is not moving on the celestial sphere, but it appears to be moving to us because the Earth is rotating on its axis.
Sir, so basically a free gyroscope which we make it point towards any point in the sky, it will behave, it will go in this yellow circle direction because of the rotation of Earth, not because something we are doing.
Yes, that's correct, beta. That is right. अगर अर्थ रोटेट करना बंद कर दे तो वो इसी पॉइंट पे, एन पॉइंट पे ही रुक जाएगा.
Okay, sir. Okay, sir. What we are doing, we are only rotating that the medal was spinning wala, nothing else.
Yes, that's right. हमने तो सिर्फ उसको स्पिन करके छोड़ दिया है. ये मोशन वो अपने आप ही बना रहा है बेटा, because of its property.
Thank you, sir. Thank you.
Okay, great बेटा, very good. So हमने इसको अंडरस्टैंड कर लिया है. Now we will be going into the tilting and drifting. तो बेटा let's take a short break. एक 5 मिनट की ब्रेक ले लेते हैं and we will go into tilting and drifting. Right? Okay, all right. So let's move ahead. We now move into the detail of tilt and how to calculate the tilting using a formula.
Sir,
Tilt is the angle of elevation or depression of the spin axis. Go ahead, beta.
Sir, ये just had a doubt regarding this. ये जो आपने star select किया है, is it like some kind of circumpolar body, because it is always above the visible horizon, ना?
हाँ बेटा, fortunately जो हमने select किया star, it was a circumpolar body. Not that we wanted to select a circumpolar star. हमने सिर्फ बेटा इस spin axis को horizon पे रखा. Horizon पे क्यों रखा? Because we don't want to point it up or down. We want it to remain horizontal. इसलिए हमने इसे horizon पे रखा. And we pointed it towards north direction, because north is what we want to find using a compass. North is our reference direction. So that is why we picked up this end point, because of this thing. And when we picked up this end point, we observed that the star was moving in a circle like this.
In all cases, sir, this will be like this only, or the gyroscope can select any of the stars?
Beta, gyroscope can select any of the star. It all depends upon कि जब आपने उसे switch on किया है तो spin axis की direction क्या है. If it is pointing at this particular point when you switched it on, okay, where the cursor is right now, तो ये ऐसा एक circle बनाएगा, bigger circle, and it will come down here, somewhere here.
Okay.
Okay. Okay. So let's go to tilting and drifting now. We now move into the detail of tilt and how to calculate the tilting using a formula. Tilt is the angle of elevation or depression of the spin axis above or below the horizontal, equivalent to the true altitude of the gyro star. The rate of change of tilt of the spin axis is known as tilting. In short, it is known as capital T small g, Tg, and it can be calculated by using the formula. The formula is tilting is equal to 15 degrees sine of azimuth multiplied by cos of latitude per hour. So azimuth is basically the azimuth of the gyro star at any particular instant, or the azimuth, or you can say the drift of the spin axis, and the latitude is the latitude of the observer or wherever the gyro is placed. And this value which we will obtain is basically the rate of change of tilt or tilting per hour. So in 1 hour, the tilt is going to change by this much of a value. The azimuth which is used in the formula is used in the quadrantal notation, not in the 3-figure notation. And the formula gives us the magnitude of tilting. How do we obtain the direction of tilting? We know that tilting will be upwards or positive if spin axis or gyro star is east of the meridian. We have seen in this particular diagram, whenever the gyro star is east of the meridian, the tilting is always upwards. And whenever the gyro star is west of the meridian, that is from Bravo to Charlie to November, the tilting is always downwards or negative. So tilting will be upwards or positive if spin axis or gyro star is east of the meridian, and tilting will be downwards or negative if the spin axis or gyro star is west of the meridian. Clear up to here, beta?
सर
Go
ये
ahead, beta.
above the horizon कैसे सर, मतलब above the horizon में ही tilting downwards भी हो रहा है ना, in the explanation, in the definition.
ओके. अब देखो बेटा, टिल्ट और टिल्टिंग दो अलग अलग चीजें हैं. ओके, tilt is basically equivalent to the altitude of the gyrostar, right? The gyrostar can be above the horizon. इस केस में तो below the horizon नहीं जा रहा है, but if you pick up another star, it may go below the horizon also. So tilt can be above the horizon, tilt can be below the horizon. इसको हम लोग बोलेंगे up tilt और down tilt, right बेटा?
Okay sir.
जो tilting है बेटा, tilting is the rate of change of tilt. So tilting is basically the motion, whether the tilt is increasing or decreasing. Okay, rate of change of tilt. The relationship is something like the relationship between speed and acceleration.
Sir, what I've understood, tilt is how much up or down with respect to horizon. Tilting is going up or going down.
Yeah, that is correct, beta. Tilt is the instantaneous position of the star or the spin axis with respect to the horizon. Tilting is the motion. Okay, like in this entire yellow circle, the tilt is not down or negative anywhere. The tilt is always up. At point n it is 0. Other than n, everywhere the tilt is up. But the motion is not upwards all the time. The motion from November to Alpha to Bravo is upwards, whereas the motion from Bravo to Charlie to November is downwards. So tilting is upwards from November Alpha Bravo, and tilting is downwards from Bravo Charlie November. Tilt is not down in any case.
ठीक है sir, okay.
Okay. Now this is a very, very important formula and will help us in understanding converting a free gyro into a gyro compass. Now moving on to understanding of the drift and the drifting formula. Drift is the direction in which the spin axis points with respect to the true north. It refers to the azimuth of the gyrostar. Whatever is the azimuth of the gyrostar, same will be the drift of the spin axis. The rate of change of drift is known as drifting. In short, capital D and small g, dg, is represented as drifting. Now drifting can be calculated using the formula. Drifting is equal to 15 degrees sine of latitude per hour. Now the formula is going to give us the magnitude of drifting. That means in 1 hour, how much is the azimuth of the gyrostar going to change? Or how much is the drift or direction of the spin axis going to change? How to find out the direction of drifting? We have already seen this in the diagram. The drifting is easterly or positive if the spin axis or gyrostar is below the pole. As you can see in this diagram, from point Charlie to point November to point Alpha, in this semicircle, the gyrostar or the spin axis is below the pole. The height of the pole is represented by the green line, and whenever it is below the pole, the drifting is easterly. It is also considered as positive, a sign convention which we use. And the drifting is westerly or negative if the spin axis or gyrostar is above the pole. As you can see from point Alpha to point Bravo up to point Charlie. In this semicircle A to B to C, the gyrostar or the spin axis is above the pole, above the green color line, and in this case, the drifting or the motion of the star is in the westerly direction. So this westerly drifting as per sign convention is named as negative or is referred to as negative drifting. Now, not required in the understanding of the gyro compass, but just for your information, this formula seems to be very, very simple. Drifting given by 15 degrees sine of latitude per hour. Now, there is one restriction or limitation of this formula. This formula is only applicable if the spin axis is almost horizontal or the tilt is close to 0, or the spin axis is pointing close to the horizon. But in our case, this limitation does not affect us. It is appropriate for gyro compass because the gyro compass is designed in such a way that the spin axis always remains close to the horizon. So we will not be or cannot use this formula to find the drifting of the star throughout its motion, but it is appropriate for us for the purpose of a gyro compass. Clear up to here, beta? Very good. Now, the last thing before we close the presentation, we have now understood the motion of the gyrostar, and we know our spin axis is going to follow this motion. We have understood how the gyrostar changes its altitude and azimuth, and with reference to it, how our spin axis changes its tilt and drift. Now, let's assume that we want to make a gyro compass. We have a free gyroscope, and what we do now is we point our spin axis on the horizon. You see this blue color line is the horizon. So we point our free gyroscope spin axis on the horizon and exactly in the north direction. You can see the laser pointer on the screen. This represents the north direction. You can see it is exactly below the pole and it has zero tilt. It is pointing in the horizon. we want our compass to point towards north and we want our compass to remain horizontal. Now, if we take the spin axis to this particular location, we know it will, as soon as we leave it, it is going to follow the gyro star. So after some time, you see, it is going to change its azimuth. The star is going to change its azimuth. The star is going to go in the easterly direction. It will be following the declination circle. So after some time, you will see that the star is moving in the easterly direction and the star is going to increase its altitude. So after some time, the star will be exactly where the laser pointer is right now. So please keep this thing in mind. This is very, very important for understanding the gyro further. That as soon as you leave the spin axis, which was initially pointing north and on the horizon, after some time, it will point in the easterly drift with a easterly drift and with a positive tilt. It will move eastwards and it will move upwards. So this is how the spin axis is going to move. And once we understand this, then we are able to control its motion. We will be able to understand how we control its motion. So that brings us to the end of the presentation. So beta, up to here clear? Any doubts coming in? Very good beta, great. So I'm closing down this presentation. Now we are moving on to the next step. ओके अब मुझे एक बात बताओ बेटा, हमने टिल्टिंग और ड्रिफ्टिंग के फॉर्मूलाज जो हैं वो देख लिए हैं. नेक्स्ट जो कॉन्सेप्ट अभी आगे आ रहा है जायरो में, दैट इज हाउ टू कंट्रोल द जायरो कंपास. ओके, सो इसमें हम लोग टॉप एंड बॉटम हैवी अरेंजमेंट जो है वो जायरो पे लगाएंगे. सो आर यू कंफर्टेबल बेटा? ज्यादा ओवरलोड तो नहीं हो रहा? हाई लेवल अलार्म तो नहीं आ रहा? ओके ना?
ओवरलोड सर, ओवरलोड आज के लिए सर इनफ.
ओके, बिकॉज जो आगे कॉन्सेप्ट आने वाला है उसमें एक चीज आपको समझनी पड़ेगी. यू विल हैव टू अप्लाई द लॉजिक और you need to be a little careful for understanding it. That's why I asked.
Yes sir. Sir, required your notes also sir.
हाँ, नोट्स तो मैं भेज दूंगा बेटा, नोट्स मैं भेज दूंगा. So you want to stop here?
हाँ सर, थोड़ा ज्यादा हो गया. कोई इजी टॉपिक है तो चलेगा सर, बट कोई इम्पोर्टेंट है तो नहीं हो पाए.
No बेटा, easy. Let me see. Yeah. Just a minute. आगे बेटा हम लोग इसे कंट्रोल करने वाले हैं. वी आर गोइंग टू कंट्रोल द जायरो. कंट्रोल करने के लिए या तो टॉप पे एक वेट लगाएंगे, यू सी दिस रेड कलर वेट, और जब ये टॉप पे हम वेट लगाएंगे, ये ऐसे कुछ वेट लगेगा, एंड जब ये टॉप पे वेट लगेगा तो बेटा ये इसकी जो मोशन है, इस मोशन को कंट्रोल कर देगा. इट विल ब्रिंग इट बैक टूवर्ड्स द मेरिडियन. So this is what is the next topic. Okay. So this is going to take some time. So ठीक है बेटा, no problem. We can keep it for tomorrow. No issues. Easy topic in between लाके कोई फायदा नहीं है बेटा. That will be more of a distraction. So no problem. We can stop it here for today. I will send you the notes also. Just go through the notes. Let this settle down well. And कल मैं आपको ये पहली चीज कराने वाला हूँ. This is known as top heavy and bottom heavy control. And इसके बाद हम gyro को कंट्रोल करने वाले हैं. So I believe top heavy, bottom heavy, controlling the gyro, and then damping the gyro. These three topics hopefully we should be able to complete. Okay. So we can stop here today.
Thank you.
Together.